Today we're going to introduce the idea of functions. Functions are anything that takes one input to one output. And as a result, they're very commonly used in a variety of different programming applications. They're an easy model for us to think about in terms of math. I like to think of them as number transformers. So with these number transformers, that's just one type of function you could have, one that takes a number and transforms it into other numbers. But there's other ways you can think about applying functions. Like think about, for example, my Amazon Echo. If I was to say, tell me the name of a song, it's going to take that input, which is my voice, an audio file, and it's going to transform it into an output, which is an audio file where it's speaking a certain answer to me. So it's transformed one thing into one thing. There's no ambiguity, there's no confusion. It knows exactly how to function. And similarly, you can think of this like with computer programs. If you were to enter in a command like, I don't know, run Microsoft Word, it's going to open up one and only one application. So these functions pop up in a variety of different applications, also in business, because in business, at the beginning of the day, my boss would come over and ask how many people we needed to bring on for overtime this weekend, and I would need to do a calculation and give him a certain number. That was the function. The function I had done was taking the input of however much we had to do that day and transformed it into how many people did we need to call on for overtime. And when you have no ambiguity, that one input turns into one output, that is what a function is. Now, the idea of functions being just about numbers is not true, because functions are anything that takes one input and takes it to one output. That's the critical detail. In order for something to function without ambiguity, you have to go from one thing to one thing. So let's take a look at an example over here that's maybe a little bit more of a broad case, and we'll get the idea behind it. So here I'm going to have two bubbles, and these bubbles are just thought bubbles, but contained within these are a number of things that are about to be transformed and things that are going to be transformed into. So you can see on the left-hand side, I've got 1, 2, 3, 4, and 5. The numbers 1, 2, 3, 4, and 5. On the right-hand side, I have the numbers 1, 4, the pound sign, a happy clown, and the name Kevin. Well, we can describe any function we want here that connects one of the things on the left to one of the things on the right. And we could say, okay, we want 1 to maybe transform into 1. We could want 2 to transform into the number sign. Maybe we want 3 to transform into the number sign as well. That's fine. We want the number 5 to turn into the name Kevin. But what we created here is a function. How do we know? Let's go through what the definition is that we just created. We're taking one thing and turning it into one other thing. That's the only detail we need to make sure happens here. And so let's take the number 1. We transform 1 into the number 1. That is not ambiguous. We know exactly where it's going. Great. What about the number 2? The number 2 transforms into the pound sign. Again, not ambiguous. What about 3? 3 transforms into the pound sign. We have a repeat there, but is it ambiguous? Not at all. We still know exactly what to do. And in case this feels a little bit weird, think about some of the things that you could program into a computer. Like, for example, if I wanted to talk to my Amazon Echo, I would say something like, what is the name of my shirt? And it would say, I don't have an answer for that. And I would say, okay, well, what is the color of my carpet? And it would say, I don't have an answer for that. The computer is programmed very well. It doesn't have an ambiguous answer as a result of these questions, but it absolutely can repeat the same answer for different questions. So it's not about having a repeat. It's about, do I have ambiguity going from one thing in my input to its resulting output? Now, what about the number 4? The number 4 doesn't go anywhere. Is that ambiguous? Again, it's not ambiguous. So this does actually still constitute a function. It's just a function that doesn't work well with the number 4. Again, let's go back to the idea of the Amazon Echo. This would be the equivalent of me queuing it up and having a dog bark into it. I don't know that I will get a reaction from the computer. So that just means that it's not something that it can even handle. But there's no ambiguity. Nothing is ambiguous. And the number 5, of course, can go to the name Kevin. So we can talk about many objects being on the back end of this function. But that's where I want to get into, is it's not, I don't want to use improper language for too long. So let's start to give it some technical names. There are this pile of things that we start with over here can normally be parsed down to just the important details. For example, the number 4 here is not important, but the number 5 obviously is, 3, 2, and 1 all are. And so we describe these as being the domain of the function. So here's the domain of the function. And when we're talking about many different detached objects, we'll often use some curly braces. These are called braces. We'll use this symbol, which appears on your keyboard above the enter key probably. And you can say 1, 2, 3, 5. And it's a nice condensed way of saying I just have a pile of elements, objects. In that pile is the object 1, the object 2, 3, and 5. For the range, very similarly, we can say that there's a pile of things that are in the range. For example, 1 is going to be a result. Pound sign is going to be a result. My name is going to be a result. So in that pile, what do we have? 1, the pound sign, and my name, Kevin. Now notice we don't need to repeat the pound sign, even though it's in here twice. It's an output for both 2 and 3. We don't need to put it in the pile twice. It's in the pile. Once I understand and have programmed my Alexa with everything that it can possibly respond to, I don't need to program it again. I just need to say that it's already got that thing, and I'll reference it if I need. So this is our domain, and we also now have our range. Now, there are a few ways that we could, of course, break this. So let's talk about now, as mathematicians, how we will break this scenario. Well, what if I connected 5 to also go to Happy Clown? Have I introduced ambiguity? Well, what is the function of 5? What is the function of 5? 5 is supposed to take me somewhere. Where does it take me? And when you say it takes me to both Happy Clown and my name, we have broken the scenario. This is no longer a function. It is a relation. I have related all these things by connecting lines between them. So that, not to say that we can't have this be a situation, it just doesn't get the elite status of function, because a function is anything that unambiguously takes us from a question that is valid to an answer that is valid. Let's look at a couple examples of functions. So, for example, we can think of functions as this new way of communicating the story that is a certain situation in mathematics. Remember that functions are number transformers if they take a number and transform it into another number. So let's think of a situation like an equation that we're aware of, like maybe the area of a circle. So we could think of the area of a circle and how that's equal to pi times r squared. Now this is taking one object to the radius of a circle and transforming it into a different characteristic, the area of that circle. And so we can think of the area as being a standalone thing. But imagine if we were going to code a computer and we wanted to teach a computer how to calculate the area of a circle. We might title the computer program, this is the area of a circle program. And we might say that it's going to depend on r. There we go. So the way that we write this in shorthand in mathematics is that we say that this is an area function. So we're going to say that this entire title can be condensed down to just a, and it depends on an input of r. In other words, it's a function of r. So if we write instead a with parentheses r inside equals pi r squared, we have a slightly different story. And I know it looks the exact same, but again, it's not about how things look, it's about the meaning behind the model of logic. What this says is that you have this number, this a number, and the area number is the size of the circle given a certain radius. What this one says is that a is a process. It's a title given to a function, given to some steps that start with r. And those steps are, take r, square r, multiply the square by pi. So whenever you see a notation like this, where a is a function, it's really capturing that you have a story going on behind the scenes. Now, the confusion that a lot of people encounter is that they say that this looks a lot like multiplication, that this looks like you're doing a times r, but that's why we have to be very careful in math that what we're not playing with is the appearance of the math, but the meaning behind it. After all, a in this situation is not something I can multiply by. It's a function. It's a story. It's a process. So to say, I would like you to take the story of Harry Potter and multiply it by 3 does not have any meaning. So whenever you see something, it's important that we keep in mind that we're talking about a meaning, a model, a logic behind this model. And when we're talking about functions specifically, this notation means start with R, perform the steps titled A, and you will get the program, the function A, depending on R, or a function A of R. Now, although we won't explore this in much detail until about Calculus 3 level, there's nothing to say that you can't take a number of different inputs and have them all be inputs into a function. So take, for example, how much you would have to pay in terms of interest if you took out a loan. There are many things that could affect that model, that computer program, if we were to teach it to a computer. There is, for example, the interest rate. There is going to be the amount of money that you took out, what's normally called the principal. There's going to be the number of payments that you have on it every single year. And all of these are going to get channeled into the result, and the result is going to be the interest payment. So we can title this entire thing as either saying that you take the interest rate and the principal and the number of payments and you do some manipulation to it and that equals I, the amount, or what we could say is that we're going to use I as the title of our function and say that it is dependent on the interest rate, the principal, and the number of payments. And so thus you can see that you can actually have a function that has multiple different inputs. It's dependent on many different things. The advantage of this notation is that it allows for us to be able to have conversations about where things came from before they were transformed. So for example, let's just take a simple equation like, I don't know, y equals 3x minus 2. And let's say that we're going to plug in an x value of 1. Well, traditionally, what we would have to do is say I'm going to do an x value of 1, and if we were really being diligent with our notes, we could say that that's our prefix kind of before we attempt the problem, and then we say y equals 3 times 1 minus 2, and then that would equal into the number 1. So we would say that we have x equals 1 and y equals 1, and then that would be our story. Similarly, if we say x equals 4, then that would be us plugging in and saying y equals 3 times 4 minus 2, which would be equal to 10. And so if I asked you, what does y equal? Well, that's actually where we get into a little bit of difficulty, because in this first line, you have the situation x equals 1, y equals 1. On the next one, you have x equals 4, y equals 10. And so if you say y equals 10, there's a lot of possible confusion where I might think that the y you're referring to was for the first problem versus the second problem. And you might be able to see how if you're writing letters, especially back in the 1700s, or if you're communicating with people in general, that if you were to just start to make the shorthand or talk to people inside conversations, they might start to say one scenario's answer when really they're trying to talk about the other scenario's answer, because y, when you remove it from the context, doesn't have a lot of meaning. But let's look at the function notation instead. Let's imagine that we wanted to give this entire story up here the title of f. So we're going to call this a function now, and we're going to give the title of f. So this is going to be f depending on an input of x, which means that it's the exact same thing we saw above, but now we're just going to change in our mind that we're referring to this entire situation as a series of steps, not as an answer. So if we now look at this as a series of steps, instead of looking at x equals 1 and writing that, we can just write what is f of 1. Notice I'm replacing the x with 1, and similarly I'm going to do that throughout the entire notation to just keep this all nice and organized. So we're going to say 3 times 1 minus 2 equals, well, that would be what? 3 minus 2 would be 1. So if I wanted to make this nice and abridged, I could say f of 1, the function f at the value of 1, which we abbreviate to f of 1, is equal to 1. And then similarly, we can do that entire thing with 4. F of 4 is equal to 3 times 4 minus 2, which is equal to 10, which means f of 4 equals 10. Well, this is a nicer notation. Now it's not about what is y, and it's not what is the function. The function is the series of steps. What is the function evaluated at 1? What is f of 1, in other words? That would be 1. What is f of 4? That would be 10. So we get a better language where we begin to describe things based on their steps, based on the story that's happening behind them, not just in terms of the result.